Okay. So thank you for coming until the bitter end. Okay. So this the first hour will be about open problems, and the second will be surprise. The second hour. Okay. So the first few open problems about Calderon's problem, I mentioned some of them already, but let me make them. Yeah. So the yeah, by now you have seen this many times. Equal to F, and then you define the Dirichlet to Neumann map to be, this is the unit outer norm. I'm not going to repeat. So the inverse problem is, Calderon's inverse problem is to recover gamma from lambda gamma. As usual, it has several parts. Uniqueness as the basic question, and then stability, reconstruction, numerical algorithm, and the range, which I'm going to talk a little bit more. So uniqueness is known I mentioned several results, but for instance, in dimension bigger or equal than 3 is known for W1 infinity conductivities. So this is uniqueness. That means Lipschitz. So this means the conductivities are they have one derivative in L infinity for alpha less or equal than 1. Sorry? Isotropic. This is isotropic for the moment. Yeah. And also is known for in dimensions 3 and 4 for W1n. That means one derivative in Ln. So the uniqueness question, let me write it here, gamma 1 equal to log by gamma 2. Does this imply? But again, I repeat, this is just the basic question, and you have a good uniqueness proof, you should get stability and reconstruction. Okay. So the conjecture is that this is optimal. So it has already been proven in dimensions 3 and 4. And so 3 is the main dimension in this case, but the main question is whether it's false for conductivities having less than one derivative in some sense. And the reason for that is because in dimension 3, there is no counterexample. So this is to find a counterexample. And the reason why is believe that this is maybe optimal. So, is that unique continuation from the boundary is not true in dimension 3 or higher. So unique. This is for conductivities in C1 alpha. These are Holder continuous at one derivative, which is Holder, alpha between 0 and 1. And this is their counterexamples. Unique continuation from the boundary means you have an open set here. You have a solution of the equation on omega, and gamma is in C1 alpha, and U in this open set, and the normal derivative in the open set is 0, implies U equal to 0. This is not true in dimension 3 or higher.
In that case, so we have counterexamples.
Counterexample. But it's counterexamples. But this is one solution. This is counterexample constructed by Miller. So that, however, in dimension 2, is unique continuation from the boundary is true. So that's why the result is gamma is an L infinity in 2 dimensions. It's always positive. I didn't say it here. If you have this equation again, let me write it in. Divergence gamma gradient U equal to 0 on omega. Suppose U at subset of the boundary is equal to the normal derivative. Of course, it has to be non-empty. Is equal to 0 implies U equal to 0. So there is a significant difference between 2 dimensions and higher dimensions. And if you recall now the result of Stala-Pivarinta in 2 dimensions, you take 2 conductivities in L infinity. Again, they are always positive. And lambda gamma 1, lambda gamma 2 implies gamma 1 equal to gamma 2. So that's uniqueness. Also, the stability has been proven and reconstruction as well. So that's the difference between 2 and higher dimensions. Here, unique continuation from the boundary is called from the boundary because this is 0 on a piece of the boundary. That's enough to guarantee the solution is 0. The difficulty for the Dirichlet-Neumann map is this is for an infinite number of solutions, not one solution. Yes. Sorry? Where? Huh? What is what? I don't understand the question.
Lower bound of gamma I.
Is lambda gamma 1 equal to lambda gamma 2? I have been using this notation all the time.
I was talking about something else.
Oh, okay. Okay, so that's open problem 1. But part of this problem is this more important, as I already said this, the counterexample here is bound not to be physical. I believe that for physical examples, uniqueness should be true. So that's what I say in the second part. Is uniqueness valid for I cannot move it up and down. Here we go again. I cannot move it up and down.
Okay.
How did you move it up and down? This is my problem. See that?
Use
See?
one finger.
Oh, one finger.
And then hold it. Oops.
it N for pan?
But the line is too far to the... I'm not liking this anymore. Okay. Okay. So what I was saying is that it's piecewise smooth. This is a very reasonable assumption, which is valid for many medium. For instance, in the human body, is likely to be piecewise smooth, or at least has jumps. So the conductivity may have jumps, but along well-defined sets. So I believe that should be true in that case for piecewise smooth conductivity. That would be a very nice result.
Any result piecewise constant?
Piecewise constants, yes. In fact, piecewise analytic is known. So let me just, since you asked the question. Okay. Questions? You know, you just need to solve one problem by the end of the summer. One. Otherwise, you don't get reimbursement. Okay. So open problem 2. This is in 2 dimensions. I mentioned we know a lot about the Calderon's problem. We know uniqueness for L infinity. There is the reconstruction, numerical reconstruction has mostly done in 2 dimensions. There is stability reconstruction, and we have complex analysis, which is very helpful. But there's a question where we have no idea which is the range of this map. So this is called the characterization problem. Because by now, of course, by now we know the domain. The domain should be L infinity. Right? Because uniqueness has been proven for this case. And sorry, this is maps from H1/2 to why is not erasing? Not erasing now. Oh, now so these are maps that sense H1/2 to H-1/2 of the boundary. So this is the map. This is the operator. What is the range? Of this map? For the X-ray transform, which is a linear map, this is a linear map of the X-ray transform, radon transform. There are characterizations of the range, depends, of course, on the domain. But here we know the domain because that's where uniqueness is whole. But what is the range? It's important because, as I mentioned during the lecture, when you have finite amount of data in practice, and so you would like to project that finite amount of data to the range so that comes from some conductivity. Right? So that's the range question is not just of theoretical importance, it's practical importance. And we know that this has to be non-negative, so that means this is always positive. This is alpha joint. But besides that, we know very little what should be the range. So here, new ideas are, and also it's open in dimensions 3 or higher, but in dimension 3 or higher is we don't know yet well what is the domain, because we don't have optimal regularity for the conductivity. But in dimension 2, one should be able to solve this. Okay, so there you are, open problem 2. Okay, open problem 3. I didn't talk a lot about this. This is a problem that is a thorn in my heart. I have tried to do this for a long time. I mentioned several applications here, optics, acoustic, quantum scattering, Maxwell equations, and others. At fixed energy, this is the important thing, is fixed energy. We're not taking high energies here. I mentioned this application, but elasticity we have not been able to do it. It's a system, even isotropic elasticity, is a system which describes the small displacements of an elastic medium. So suppose you have a displacement and you measure what's called the traction. So it's the displacement to traction map. That's the analog of the Dirichlet-Neumann map, which is described here. This is the unit outer normal. Can we recover from this map the two parameters? These are called Lamé parameters, lambda and mu. Can we recover them? Again, it's not just uniqueness, but the uniqueness is the basic question, stability and so on. We know it if mu is close to constant, but that's it. And if we know one of the parameters, lambda or mu, we know the other one. But the two parameters, we have not been able to prove it. This is an important example. Many mediums are elastic. And this is what you mentioned. Please stop me for any problem you want to know. Okay. Problem 4, still we are in Calderon's problem. The partial data problem. I mentioned this. It's one finger. Oh, it works. So you had two open sets. I think I called them gamma and gamma prime this time. Before I called it gamma 1 and gamma 2. And they can be the same. So suppose you measure the Dirichlet-Neumann map restricted to gamma for when is the support of F. You measure the current on one of them, the support is contained on the other one. So it's grounded on the complement of gamma prime, and then you're measuring the current only here. So gamma, important case, as it says here, is gamma equal to gamma prime. And I mentioned these results yesterday. There are some partial results in dimensions 3 or higher, but we don't know. Even in this case, gamma is equal to gamma prime. We don't know the answer to this in dimension 3 or higher. In dimension 2, we do. And of course, we would like to do it more generally, but first solve this case. And these results are based on new CGO solutions, constructing complex geometrical optics solutions, and one uses Kahneman estimates for that. Okay, so this I already talked about this. Okay. I mentioned that there is a method to find obstacles. There is this complex spherical waves here that you send spherical waves from the outside, and you can distinguish you can begin to see the boundary here as you do for enough points, where the conductivity jumps and how you can also determine how much it jumps. But in general, the obstacle problem, you have here a domain inside another one. Okay? So suppose Q is smooth in omega man. This is an inhomogeneous median outside D. You can assume another regularities you want, but let's take a smooth, and you take what's called the Cauchy data. I think Rui defined this. Is U restricted to an open subset of the boundary outside, and the normal derivative, well, this is a solution of the equation here. And the support is contained here. Can we recover Q? Okay. Can we recover Q here? It is known that from this information you can recover the domain. But this is n-1 information. But can you recover the median? And also you would like to recover both. The domain here, I mean the Q here in between, and the obstacle, D. So an important point here, the support of U is contained in here. So U is 0 in the boundary of D. So it's very difficult to construct CGO solutions with value 0 in a closed set like this. That's the difficulty using CGO solutions. You can take V to be the whole boundary if you want, but the U is 0 on the boundary of D, so that's why it's called the obstacle problem. In dimension 2, you can solve this. This problem is solved. Questions? This will be available on the web. All of these problems will be available. Now we go to the anisotropic case. Remember that there is this invariance. As long as you have the equation invariant of the changes of coordinates, even if you have an isotropic one here, you change coordinates, you will have an anisotropic conductivity. But suppose the conductivity gamma is anisotropic. Then we observe that the Dirichlet-Neumann map for the push forward of the conductivity is the same as the Dirichlet-Neumann map for the conductivity itself. So you have a change of variables, which is the identity of the boundary, the diffeomorphism, then the push forward of the conductivity in terms of matrices, given the Jacobian transpose composed with gamma, composed with the Jacobian, composed with psi inverse, and that gives you the same conductivity. So the question is that the only invariance? And this is solved in dimension 2, as Rui pointed out yesterday, and I also pointed it out. But it's wide open. This is the $2,000 problem, right? To remind you, you take two anisotropic conductivities, and they have the same Dirichlet-Neumann map. Thus, there exists a change of variables, which is the identity of the boundary, so one is the push forward of the other. So this is known for real analytic conductivities, but it's not known even for the smooth conductivities. The question at this point is not optimal regularities, even for the smooth ones, is not known. I made a lot of emphasis on this problem. If you know this, then, as I mentioned previously, then in practice, you know some information about the conductivity, anisotropic conductivity, so you might be able to fix the change of variables. Okay, and related to that, a sub-problem of that is, remember for isotropic conductivity, we reduce it to the Schrödinger equation. And U at the boundary is safe, assuming that this has unique solution and the Dirichlet to Neumann map is the normal derivative of the boundary. But suppose we have a more general metric. So G here is the conductivity. You can think of the conductivity or a Riemannian metric, so positive definite symmetric matrix. The anisotropic case is the same as the anisotropic case. I wrote it there as a metric because it's a metric, positive definite symmetric. Consider, suppose you know the metric. In this case, it's not a problem of recovering the metric or the metrics. You have a potential here, given data F, and you define the Dirichlet to Neumann map to be the normal derivative. Can you recover the potential from the Dirichlet to Neumann map? Of course, we would like to recover both. Again, this is a problem in dimension 3 or higher, I should have said here. This is n bigger or equal as. The reduction is in every dimension, but this problem is in dimension 3 or higher. In dimension 2, this is no.
So in the fixed metric, it's known or not?
The metric G is known. Of course, you would like to recover both, but we don't know that even for Q equal to 0, right? That's the previous problem. So we fix the metric, and we want to recover the potential. This corresponds when you take a multiple of the anisotropic conductivity, alpha is a function, positive. The question is whether you can recover the multiple, the conformal multiple. You can reduce it to the potential. The potential is, as we saw before, the Laplacian square root of alpha or the square root of alpha, Laplacian G. Okay, there is a particular case where we know how to do this as called conformally transversal anisotropic, which is a multiple. This depends on all the variables. That's conformal. Multiple means conformal. And the matrix has a form 1. And in the n-1, the n-1 and n-1 part here, this is 0, 0 here, is independent, is positive definite, symmetric, but is independent of x1. So there is one direction which is Euclidean. And in that case, you can prove, if the metric is of this form, you can prove that you can recover the potential. For examples, important examples of this, of course, the Euclidean metric, this shows the previous result that you can recover the potential from the Dirichlet to Neumann map. If this is just C of x times the identity matrix. But you can write the metric like this after changes of coordinates for the sphere, for the hyperbolic plane, but it's very special, and there's very special conditions. The general case, we don't know it. And this is, here is an easier problem because there is no diffeomorphism invariance. You don't need to find a diffeomorphism, the change of variables. It's just recovering the potential from the Dirichlet to Neumann map. Okay, so this problem relates to the second part, which was the Gelfand problem. So remember, we defined from the wave equation, we show, let me write it here. Questions? Now we was to the second topic, the Gelfand problem. And that corresponds to taking the wave equation for the Laplace-Beltrami operator. So you have omega cross time. Let's say infinite time. It doesn't, for the purpose of this, is equal to f, u is equal to 0. At 0, or is 0 in the far past. So this is Laplace-Beltrami operator, or anisotropic conductivity in dimensions 3 or higher. So this is, it's called the Laplace-Beltrami operator. Okay, and when we can define the Dirichlet-Neumann map for the hyperbolic problem. The hyperbolic problem, you have all the frequencies. The elliptic problem, you have a fixed frequency. This is much better pose. And then the boundary control method, an example of this, or I should write it here, is an important example is acoustic equation. You can add lower order, one should add lower order terms, but let me just, is this equation. The acoustic equation with C is possible. That's the isotropic case. Right? Oh, I forgot to write something here. G upper ij, when G upper ij is the inverse. Okay. So, and then we show using the progressive wave expansion or geometrical optics that from the Dirichlet, so you can define the Dirichlet-Neumann map. Let me do it for the sound speed. Suppose you do the same for the sound speed. Is the normal derivative at the boundary. Again, you give boundary data f, the same thing, and use 0 for. Okay. So we show that from using this expansion, remember A0. This is geometrical optics. Delta t minus phi x omega. This corresponds to the distance function. So we show that in general, you have a domain with a positive definite symmetric matrix. You can recover from this information, you can recover the distance function between boundary points. So that's the infimum of the length of all the curves joining x and y. Maybe I will remind you here. This is the infimum of the length of for all the curves joining the points x and y. You can again think of a domain in Euclidean space. And this is the length of the curve, and is given here in local coordinates. So the inverse problem is to recover g from the distance function. Again, you have a diffeomorphism. It was called the pullback. The matrix pullback conductivity is pushed forward, but this is very similar to what we had before for the anisotropic conductivity. That's the boundary rigidity problem, and then we needed some condition to guarantee that you can recover the metric from the g from the distance function. Okay, and one condition that we impose is that it's simple. So given 2 points in the boundary, there is a unique minimizing geodesic joining the points, and the boundary is strictly convex. So there are no geodesics coming together. As I said before, we want to get rid of this condition, but that's the first case that one should solve. And the conjecture is that if this is simple, then it's boundary rigid. That is, from the distance function, you can recover the metric up to the natural obstruction. Okay, so this was posed by René Michel and has been solved in dimension 2. In dimension 3, we know for metrics closed, this is a local result to a dense and open set, so it's a generic condition. But recently, we solved it for simple metrics with non-positive sectional curvature. Remember, I mentioned this result, and metric with no focal points. I mean, remember this foliation condition? It was a foliation condition, and it's satisfied in these cases. Okay. And actually, a more general result was shown. The length rigidity problem. So you take a point and direction of geodesic, you follow it, you send it to the point of exit, direction of exit, and you measure the length of this geodesic as well. So in that case, the question is, can you recover the metric in size, the matrix G? This is called length rigidity. So we solve this in dimension bigger or equal than 3 if this foliation condition is satisfied. Remember, the foliation condition was that the outside manifold is strictly convex, and you can foliate it by strictly convex hypersurfaces. So you solve the problem locally first, and then you continue until you fill out the manifold. And the foliation condition is satisfied. So this is the problem. It's still not solved completely, because we assume this foliation condition, right? The reason was because of the method that we used. We solved the problem locally, and then we went further and further. Even in dimension 2 is not solved, because in dimension 2, what we have is in dimension 2 is assuming that it's simple. So there are no caustics, no conjugate points of the metric. But the foliation condition allows for caustics, any kind of caustics, in fact. Right? So we will solve the problem, we will prove Michel's conjecture in dimension 3 or higher if we can show the simple manifolds satisfy the foliation condition. So the question is, simple manifolds. So suppose the manifold is simple. Does it satisfy? This is a very geometric question, the foliation condition. You can solve this. This proves, this will prove Michel conjecture in dimension n bigger or equal than 3. In dimension 2 is proven. It's close, but it's no cigar yet. So I don't know the answer, because simple manifolds, we know when the curvature does not change sign. I mentioned that this foliation condition is known to be satisfied for manifolds with non-negative sectional curvature, like this. You know, when geodesics come together, the curvature is positive, non-negative, and or non-positive curvature, and so on. But this is, as I said here, the open problem 8 will be solved. You can solve this, you have a very nice paper. And this is very geometric. You don't need any background to do this. to try, at least to try. I'm not saying you can solve it, but okay. So that's my questions. Okay, that's the foliation condition. And there was also the partial data problem. That we use the partial data to do this. I mean, we solve the problem locally near the boundary. So here we're taking less geodesics, not all the geodesic joining points in the neighborhood of the point P, which is assumed to be strictly convex. And we want to recover the metric locally near the point up to change of variables, etc. But that, we prove that only for dimensions 3 or higher, because in dimension 3, you have a lot of geodesics, much more than in dimension 2. And in dimension 2, this is known, not known. So this is open problem 12. Is it true in dimension 2 that given geodesics joining points on the boundary in the neighborhood of the point P, can you recover the metric locally near the point P? Okay, so here you have less freedom, but it should be true. This is partial data for boundary rigidity. So this is, and also we show that from the transport equation, you can recover the geodesic transform of the coefficient of the amplitude of the wave when you have A0. When you went to solutions of the on this wave, let's take the acoustic equation as the same is true when you have a metric. Here, we took solutions that behave like some amplitude, delta t minus phi of x omega plus smoother terms, remember? So phi gives you the distance function, and to recover A0, you have to integrate it along geodesics. That's the transport equation. So that leads to the problem of finding a function from the integral along geodesics. This is the exit time of the geodesic. It also arises at the linearization of this problem when you are in the same conformal class, meaning you have only multiples of this metric. That's a problem of interest in its own right. In the case that the metric is Euclidean, the standard metric, the standard measure of distance, this is just the X-ray transform that has been considered a lot in these 5 days. So you take assuming that it's non-trapping, so all the geodesics exit with strictly convex boundary, you may have a little bit of trapping. I mean, this is the geodesic transform injective? It's known if the manifold is simple again. This is the famous result of Muhammedov. And in dimension 3 or higher is the boundary, it's a strictly convex boundary again, and the foliation condition is satisfied. This was proven earlier by Bashi and myself. Questions? Okay. Okay, so I already mentioned this problem. Okay, now another question about Gelfand's problem. Supposing instead of taking the sound speed independent of time, we take the sound speed dependent on time. And we're given the Dirichlet to Neumann map again. The H stands for hyperbolic, not to confuse it with the elliptic, but it's the same Dirichlet to Neumann map, but now you have the wave equation. So here the sound speed is dependent on time. For instance, a beating heart depends on time. It's not a fixed sound speed. So can we recover the sound speed? Now it depends on one more variable. And that's not known because the method that was used before for solving this is either the boundary control method or geometrical optics. That doesn't give you this in full generality. So for coefficients dependent on time, the boundary control method is not applicable unless the coefficients depend analytically on time. So this is a nice question that can we recover C of xt uniquely? Again, I mentioned primarily the uniqueness question, but of course the stability, reconstruction, and so on. It's known it's a function of x alone, and this boundary control uses the Tataru's unique continuation result. And we have seen that for equations, for nonlinear equations that depend on time, when you have a nonlinearity, then you can find the coefficients. That was the point of the nonlinearity that I mentioned. Have mentioned several times in the past couple of days. What time is it? I ran out of battery already? Is there a way to find out the time? Okay. I'm not done with the problems. Okay, so this is the point that has been emphasized many times in the past 2 days or 3 days. Again, that the interaction of waves produces new waves that give you information about the inverse problems. Okay. So I will come back to this in a moment, but I want to introduce a problem that I did not consider. I was planning to consider it, but I didn't. There is not enough time. I will have to use all the summer for. But it's a problem that I like a lot, so let me mention it, which is scattering. The problems I have considered are really problems where you are given information, you have a bounded domain, and you're given information on the boundary. The measurements are made on the boundary. Scattering, you're making measurements at infinity. So you wait a long time. So the things can be very complicated here, but then you wait a long time, things get much better. This is the philosophical idea of scattering. So, of course, I cannot develop the whole theory of scattering, but let me tell you a quick way to define the measurements. So you take for the case of the Schrödinger equation, you take Laplace minus q minus lambda squared. So lambda is a real number. Suppose this is called the potential, and there are what's called generalized eigenfunctions or outgoing eigenfunctions that behave like this plane wave. This corresponds to the Fourier transform of delta t minus x omega. You take the Fourier transform in time. This is e to the I lambda x dot omega up to a constant. So this corresponds to the first term. Remember the plane wave coming in. But I'm looking at the frequency side, not at the time. One can also define it using time, but it takes longer. So that's why I want to do it this way. I only have a very little time. And you have a coefficient here that corresponds to the next term. Remember the progressive wave expansion was delta t minus x omega plus the coefficient x omega times the Heaviside function t minus x omega plus smoother terms, right? we solve the wave equation plus the potential or minus potential using this plane wave in the past, and then interacts, and the interaction is reflected here and the other coefficients. So it's the same here, but instead of plane wave, you have a spherical wave coming out. You see in the movie that I showed, there is a spherical wave that comes out, and also very well. So this is e to the I lambda modulo of x, and it has an amplitude. So omega is the direction of the plane wave, right? And taking the Fourier transform. And theta is the direction of observation. So you let it interact with the potential here, and you observe it in some direction theta. Okay. This is theta, which is a unit vector in the sphere also. This is called the scattering amplitude. So the inverse scattering problem, maybe I will write it here. Inverse scattering is from the scattering amplitude. This is called the scattering amplitude, determine Q. Okay, and it's known, you know this for all frequencies, is true, and this follows from the wave equation. It's known for fixed energy because you can prove the following fact. Suppose you take the support of the potential is in this ball, so it's 0 here. You can prove that from the scattering amplitude, a fixed energy, so lambda is fixed. Then you can recover the Dirichlet to Neumann map in the outside of this ball. This is the ball of radius r. So the Dirichlet to Neumann map corresponds to the near field you're measuring close by, and scattering is far field. But from here, because you know the potential outside, you can recover the Dirichlet to Neumann map. This needs to be proven. So you can solve, I mentioned that the inverse scattering problem of fixed energy could be solved using these ideas, because you can reduce it to the Dirichlet to Neumann map and therefore recover the potential. So you go from the outside, you can recover all the information on the boundary, because you know the potential outside. And for all energies, or for high energies, is also known. This is the Born approximation, is called. So, so this is the Born. So the Fourier transform of Q of lambda theta minus omega. This is the Fourier transform. So if you know for all lambda sufficiently large, you can easy to recover. You can recover for every C, therefore Q. But this is very unphysical, because the equation, this Schrödinger equation, is not valid anymore for large frequencies. The model is not valid. So, this is a nice mathematical result, but not. That's why you want to consider fixed energy. So, fixed energy, we can solve this problem because you can reduce it to the Dirichlet to Neumann map. And if you want a reference about this, I can give you it's in some survey that I wrote. But the question that has resisted a lot of efforts is whether the backscattering, so you're sending the wave and you measure it in the same place where you send it. So you look at the echo. How much echo are you receiving? Can you recover the potential from that? And that's not known. And the difficulty here, this is the number of variables that you have is n minus 1 here. and 1 here, so it's n dimensions. You're trying to recover a function of n dimensions. This is true in every dimension, and the only case that we know it is in dimension 1. And this is the Gelfand-Levitan method. So there have been several partial results, but no cigar. Okay, there you have another problem that I would like to see the solution. For this one, $500. I'm just kidding. Okay, these are the. Okay, so do I have time? 5 minutes. Okay. Okay. Another because we study inverse problems for the wave equation and for the Laplace equation and the conductivity equation, and this is similar for electromagnetic waves or Maxwell equations and so on. There is some effect, physical effect called the photoacoustic tomography, which was discovered by Graham Bell. This is the same inventor of the telephone. He was trying to do wireless phones, this was in the 19th century, if I don't remember exactly. And he observed the following. When rapid pulses of light are incident on a sample of matter, they can be absorbed, and the resulting energy will then be radiated as heat. This heat, because there is an expansion, causes detectable sound waves due to the pressure variation in surrounding medium. This is the wave you hear. That's why it's called the sound of light. So light produces sound. And this is part of what's called hybrid methods, which you use two waves, two different type of waves to obtain information, because waves are sensitive to different variables. For instance, ultrasound, well, this is to bulk compressibility, opticals to the permittivity, the electrical measurements, electromagnetic waves to conductivity, and so on. So the idea is to use different ways to create an image, a better image. And this is what's happening here. This is a cartoon. So you send a rapidly varying laser pulse. So as mentioned in the photoacoustic effect, this is a physical effect. Then it hits the tissue, and that produces an elastic expansion and produces sound. So from the electromagnetic wave, from this laser, you're creating sound, and you measure the sound around this object. And from that, you try to create an image of the inside. So you have a laser, and it absorbs, creates a thermal expansion, creates an acoustic waves, and that's what you measure. And Li-Hong Caltech has been one of the main proponents of this method, and some images are amazing. You can see very detailed images of the vessels. This is, well, you could see it, and there is a melanoma, unfortunate melanoma you can see the cancer very clear. Of course, the deeper you go, the less resolution you will have, because light will scatter. And there is an interesting inverse problem here. In photoacoustic, the difference between photoacoustic and thermoacoustic, I never understood why they put two names for the same thing. It's just the frequency of the wave that you're sending in. The one is called photoacoustic when it's a laser, and lower frequency electromagnetic wave is called thermoacoustic. So you try to recover H. What H means the heat. This is how much heating is produced at the point X. Okay. So you solve the wave equation. This is how much heating. And once you know H, so this is the initial condition. This is a coefficient that depends on the tissues. We assume to be known. You want to know how much heating is produced, and then you try to recover the optical properties in the case of photoacoustic tomography or the electrical properties, thermoacoustic tomography from this information. So it's a two-step problem. Let me see whether I can get it now. Yeah, you can see it. Because blood, is very sensitive to electromagnetic waves, so you can see very clearly the veins. This is a melanoma in the hand. Okay. So so the open problem is the following. I will finish with this. Sorry, sorry we go over time. The question is, can you recover both? C, the sound speed. We don't know the sound speed. And H, this coefficient here. Sometimes you even ask for this beta as well, but let's be less ambitious. C and H from the measurements of the solution of this wave equation at the boundary. This is a linear problem. This is the initial condition. We want to recover the initial condition here. The nonlinear problem is to recover the sound speed, as we saw that's a nonlinear problem. This is very similar to the radon transform, because you can solve, for instance, C equal to 1, you can solve this explicitly as the integral over spheres of the initial condition, and you can invert that. So if C is known, we can recover H. If H is known and fixed, we can recover C. And you need some conditions here. And there's very partial results for recovering both. You cannot recover everything, because if H is 0, the solution will be 0, then you cannot recover anything. So you need some condition, but exactly what here, we don't know. So this is some partial results. I have some recent paper that I didn't mention here on this. So I have more problems for nonlinear equation, but I will write them down in the notes. For these are other problems for the first two days or 3 days. First 3 days. Okay, you have enough problems. Okay.
Any
Questions? I don't want questions for this. I want solutions.
Any solutions? All right, thanks. So we'll have a coffee break, and then we'll come back for a lab.
I'll give you the file, not for this one, because I need to complete it. But for the next one, I will give you can copy it if you want. It's number 5. This one.
But Josh, for your privacy, we are not going to share.
Yes?
So I was just wondering, the third open problem, that
Yes.
was concerned like whether an isotropic stiffness tensor determines, or whether the NMAP determines an isotropic stiffness tensor uniquely, right?
Okay.
I think I'm working with Jonas in the direction of that result for anisotropic stiffness, also for an open.
For anisotropic.
for
But it's not even
open
known.
and-
It's
no.
not even known for isotropic.
No, I know, but for an open and dense set of stiffness
Oh,
tensors.
okay,
So
okay.
I think like what we know so far is that for an open and dense set of stiffness tensors, we don't have like a